Now, the area is actually probably the easier one because that's already, usually we think about it in terms of the radius. Area of a circle relates to the radius in this way, that the area of the circle is equal to pi times the radius squared. That's the relationship between the area of a circle and its radius. Circumference, most of the time when you learn circumference as pi times diameter. But I want you to relate it to the radius. So how about pi times 2r? Or I'm just going to clean that up a little bit, 2 pi r for circumference. So that's our relationships. A circumference relationship to the radius, and area relationship to the radius. And if you're thinking, well, why specifically did we relate to the radius? When I read the problem, okay, an oil tanker spills oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. I have a rate of change for the radius. That's something I know change information about. How fast are both the circumference and the area of the spill increasing when the radius is 20 feet? Given the rate of change of the radius, I want the rate of change in the circumference. And given this rate of change in the radius, I want the rate of change in the area. So this is telling me about how the radius is changing. So that means that's a good indicator that we need R in our relationships. So if we look at my steps, I read the problem. I did not draw a picture. It's a circle that's getting bigger, okay? It's this oil spill, and the radius is growing, and so as the radius grows, the circle is growing. I've got an equation that relates the circumference to the radius. I'm kind of doing these two simultaneously, so I went ahead and wrote a relationship that relates the area to the radius. And now we're going to take the derivative with respect to time. I have a relationship between these variables. Now I'm going to relate their rates of change. If C equals 2 pi r, then dc dt, the rate of change of circumference over time, equals, now got to be careful, but 2 pi is essentially just a constant. So if I have a constant times r and I'm taking the derivative, I don't need to use a product rule when I just have a constant times a variable. So dc dt equals 2 pi times dr dt. Two pi is a constant. It's not changing. When we have a constant times a variable, we don't need to use product rule. When I take the derivative of a constant times a variable or a constant times a function, the constant comes along for the ride. Okay. All right. How are we doing? We all right with that derivative? It's weird because you're like, well, it's because it's implicit. You're taking the derivative with respect to time, and there's no time in there. You're like, because it's built in that the circumference is a change. The value of circumference is a function of time, and the value of the radius is a function of time. Okay. This piece of information, measuring how the radius is changing, that's the value for dr dt. The radius is getting bigger. It's increasing at a rate of 50 feet per minute. So if I look at my derivative equation, I want to calculate this. How is the circumference changing? It looks like it doesn't matter what the specific radius is. It only matters, the only thing I need is I need 2 times pi times the dr dt number. And so I'm thinking that my radius changing at a rate of 50 feet per minute is going to have my circumference changing at a rate of 100 pi feet per minute. As the radius gets bigger, the circle gets bigger, but the amount that the radius is changing is creating more change in the circumference. This is how the radius is changing. Because of how they're related, this then creates this amount of change in the circumference. We're measuring this at one point in time. Sometimes the exact measurement at that point is relevant, and sometimes it's not. Okay, so let's take the derivative of the area function with respect to time. What should I write? How about, let's start with this, dA dt. How about 2 pi, just r, dr dt? Yeah, very good. Derivative of r squared is 2r. Pi is a constant, so pi is going along for the ride. So when I take the derivative, like if I take the derivative of 3x squared, it's 6x. So if I take the derivative of pi r squared, it's 2 pi r. But we're taking the derivative with respect to time, and so there's the dr dt. All right, so if I'm going to finish this problem, just kind of grab this and throw it to a new page. So if I'm going to finish solving this problem, I want to find how the area is changing. I'm told that we're talking about the specific point in time when r, I believe, is 20 feet. Interestingly enough, that wasn't important in the circumference problem, but it's important in the area problem. The radius change is 50 feet per minute. This is also a good check for us as to include the units and be clear on the units, because then that tells us a lot about whether we're actually using numbers the right way. I'm looking for a rate of change of area. Area is measured in some kind of units squared. So I would expect to, but my dA dt is in some kind of square units per minute. And if I put this together, just kind of leave the pi in there, 20 times the 50 times the 2, this is going to be 2,000 pi square feet or feet squared per minute. They're all different in that they're different relationships between the variables. They're all the same in that once you get that relationship set up, you're going to attack every problem the same way or a similar way. You have the relationship, you take the derivative with respect to time, you plug in the things that you know, and you should be left. Typically, you're figuring out ultimately one of your variables' rates for change. If you have 3 changing variables, most likely you'll be given 2 of the rates of change. There are some exceptions to that, but there may be a way to figure it out. We'll always be able to find everything will go in except 1. We're not always going to be looking for this rate. We might have been told the rate of change of the area and asked to find the rate of change of the radius. And so once I took the derivative, it just would have been a difference of putting something here. This would have been what was missing, and then, work backwards. Okay. Relationship, derivative with respect to time. So change it from a relationship between variables to a relationship between rates of change, and then solve for the missing rate of change. Related rates. It's not just a clever name. Okay. All right. Let's do number 2. Oh, I always forget to change this problem. Every year I read this problem, a rectangular well, and I'm like, oh, that's stupid. It should just be a tank. Not a well, but whatever. You've got a rectangular box, and it's getting filled up with water. Right. Here's my rectangular box. Pretend. All right? And we're putting water in it. Right? As I add water, if we think about the calculation of the volume at any given point in time, certain numbers are not going to change. If I put more water in this tank, and then at any given point I stop and calculate the volume, this measurement, doesn't matter how much water I put in, this measurement is the same measurement. This measurement is the same measurement. But if I'm calculating the volume of the water, not the volume of the tank, but the volume of the water in the tank, the more water that goes into the tank, the bigger my volume will be. Got it? Does that make sense? Okay. So, I'm talking about this rectangular tank, box, well, whatever we want to talk about. And water is running into it, and we've got this measure it. All of this information is suggesting that this is a question about volume. Additionally, check out that rate. Cubic feet per second. Straight up, that's a volume change, right? Because that's how we measure volume, in cubic feet. So there's a lot of clues in the problem sometimes that you may have to decipher to figure out, okay, what is the geometry of the problem? This is a volume problem. Sometimes it'll explicitly say volume, okay, or whatever area, surface area. So how I find the volume of a rectangular prism by taking the length times the width times the height. So far, so good? Now, products are always tricky. Products can mean product rules unless you've got constants. Because you don't have to do a product rule if you've got constants. And thank goodness, otherwise this problem would be a total bear. When I put water inside of a rectangular tank, and I measure the water at any given point, that's the only guy that's changing. That's a constant, and that's a constant in this particular problem. When I pour water into this, or fill water into this tank, well, whatever you want to talk about, and then measure the volume of the water, the volume of the water will change because the height of the water will change, or the depth of the water will change, but this measurement and this measurement, length and width, if you want to call it, of the tank don't change. Does that make sense? Yes.
So you're just like determining the axis of where it changes?
You're, say that again?
Determining the axis of where the change is going to be?
Yes.
And everything else? So
Yes.
Like, wouldn't then X and Z would technically be the same then? Because you could say length and width would be the same way. So how would you distinguish between that X and Z axis? I mean, you probably would get the same answer though, like if it was changing length and width, how would you know?
Okay, so if we were in something where the length and the width were both changing, is that you're asking what
No,
if?
How would you know if you're changing the length or the width and the different numbers if the water's just going down from the
I don't know if I understand your question. Ask me that again?
So you have your box, right?
Yeah.
Can I walk up there?
Oh yeah, absolutely. I'll knock it up. Yeah. Show me what you're talking about. Because I suck visually, so yeah. So it says I'm like, what? So okay. Help me understand what you're saying.
If you're a box, you could say this could be the length or this could be the width.
Oh, it's irrelevant.
So it doesn't matter.
That doesn't matter. Okay,
so, like,
thank
if
you.
water was like coming in, you could just say from this side, how would you know to take the derivative from either the x or y axis? Would you just be told? In the
Because
problem?
okay, well, I think you're probably reading too much into it. If you think about how at any, just basically the fact that you're filling up a box with water, at any given point, if you stop and think about the rectangle that is the water, only one of the three dimensions is different when you put more water in. That's the one that's changing. Okay? I don't know if that answered your question.
Wait, just one more.
Uh-huh.
Is the length and width always going to be constant?
It would, no, it depends on the kind of shape we're talking about. Okay? So depending on what we're doing. I don't like to say yes, it's always a big, but if we're talking about something that's that's rectangular, as you put more water in, the only thing that's really different at any given point is the height, right? If you have a cylinder, similarly, you have circles, you put more water in, and you stop at any given point, the only thing that's different at any point is the height. When that's not going to be true is something that's like that, because if we put water in and stop at any given point, would have different measurement. Like if you have a little bit of water, you have like a little cone versus a lot of water is a bigger cone, and so there's more things that are different.
Okay.
Does that make sense?
Yeah.
Okay. Okay. You know I hate this. Okay, this is like one of my least. I really like these problems because they're very they are real, but I hate them because they're also visual, and I suck at visual. Okay, so length width in a rectangular prism filling up, height changing, so volume changing. Other two dimensions remain the same. So the change in the volume is going to strictly relate to the change in the height. All right, L and W are fixed numbers. They're not changing in this problem. So we know how the overall volume of the water is growing. The water is going into the well at a rate of 3 cubic feet per second. So my volume is changing at a rate of 3 cubic feet per second. So I want to know how that rate of increase in water affects the change in height. As we put more water in it, the water level is going to rise. The well's, it's 6 feet by 4 feet. And the fact that it's initially 8 feet deep, that the whole well is 8 feet deep, is totally irrelevant. The actual height at any given point, in this case, doesn't really matter what it is, because we're going to have a consistent change. Water going in at a particular rate is going to create the same level, the same amount of change in my height at any given time. This is feet, and this is feet. So when I take 3 cubic feet per second equals 24 square feet times dHdt, this is the kind of thing where you got to be careful, don't go mental. And you look at it, you get excited, you're like, woo, 3, 24. The answer's 8. But the answer's not 8. Because it's not 24 divided by 3. It's 3 divided by 24. Right? So 3 cubic feet per second divided by 24 square feet is, I like 1/8. And you could put a decimal here. I'm doing all of these right now without a calculator, but you know, if you had a calculator, you could, if you wanted to give that as 0.125, you could. So weirdly enough, the tank problem, like, this is one of the harder ones because it's, you have to stop and think that certain things aren't changing. Okay. In other problems, sometimes it's a little easier to talk about and think about what's changing and what's not changing. So volume problems, area problems, circumference problems, perimeter problems. These are all typical geometric scenarios that relate measurements where the change in one or more of the measurements will change. That rate of change creates a potential different rate of change in the other elements. That's what we're trying to do with these problems. We are actually going to, I think it would be better served, we're going to skip Tweety and the rowboat. Tweety and the, no, we're going to come back to them, but Tweety and the rowboat are kind of the same problem. They both have the same concept. But since we're doing volume, let's go to another volume and let's do the cone. Let's do the cone volume. So now it's not a rectangle. Now it's a cone. It's a conical tank. And water is coming into the tank. So, what do you need? Oh yeah, go ahead. All right. So, if you think about a cone, this is kind of what I was just trying to show Hasna. As you put water in a cone, or whatever in a cone, if we stop at different times, you basically have a circle base and a height, and you multiply that by 1/3, and that's how you get the volume of anything that's shaped like a cone. You find the area of the circular base, you multiply it by the height, that makes a cylinder, but then you throw the 1/3 on it, and that's what gives you the cone. And if you think about the water going into the cylinder, if I stop the water kind of at this height, and I've got this kind of little circle on the top, versus if I stop the water at this height with a bigger circle at the surface. So imagine the surface of the water. The surface of the water is going to be circular, but less water in the tank, a smaller circle. And the circle gets bigger, 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 and then if we fill the tank to the top, the circle has a radius of 5 feet. Are you on board with that? So, when I put water in this cone, two things are changing. The height that I'm going to use to measure the volume of the water, and the radius. Bigger circles, taller cones, two things changing. So when I look at this formula, and I realize that both of these are changing, that ups the difficulty level. And because this is changing too, right? Everything's changing. I put more water in, the height changes of the water in the cone, the radius of the circular surface of the cone water, the overall volume of the cone water, everything's changing. These are all functions of time. So that and that is in fact the product of two functions. So how do we take the derivative of the product of two functions? You've got to use product rule. Now everyone's like, just figure that out. Oh, crap. Yeah, we're going to have to use product rule and implicit. So we're going to have all kinds of nonsense going on in this problem. Okay. Unless, okay, so I'm going to write product rule. And you can absolutely do this problem with product rule. We'll come back and do it with product rule. I want to try to show a nicer way to do this. Because if you're like, oh, product rule is going to make this really long and scary and crazy, you're right, it is. So, we either have to treat this as the product of two functions in another equation and therefore take the derivative using the product rule, which we can do. Actually, I think I'm going to start that way. But an alternate plan will be, if I can relate those two functions, if I can figure out how R and H are related, if they are related, then maybe I could write the whole thing with just R or the whole thing with just H. And then that way I wouldn't have to do product rule because I'd have just one variable over here, not two. You got my thinking? It's like if I could write this just with all H's, life would be better. No product rule, just derivative of the H and the derivative of the V. Or if I could write it with all R's, all better. Because otherwise, let me just start a little bit of product rule here. Here's what we're talking about. I'm going to keep that whole guy together as one big function. Those extra numeric constants just have to belong to one function, so I'm going to have them tied onto the R squared. So if I keep the H, and then I take the derivative of 1/3 pi R squared, it'll be 2 times a third times pi times r times dr dt plus 1/3 pi r squared times dh dt. I kept my second function the same, h. I took the derivative of my first function. 1/3 pi r squared's derivative is 2 times a third times pi times r times dr dt. Plus, I kept my first function expression the same, took the derivative of my second. The hard thing you're thinking, you're like, they're not functions. They are. They're functions of t. They're not explicitly shown that way, but it's implied that radius and height are two things that are changing as time changes. They are functions of the time. Ian, talk.
Can we just like solve it to make it easier, just keep it, take 1/3 pi out and just like function?
Take them out, like factor them out?
Yeah.
Yeah, I mean, we can absolutely do that. We can't throw them away.
Oh, yeah, no.
But yeah, I mean, we could move them over to, yeah, so we could have, put those constants over there, over on the left side, and then just taking the derivative of r squared h, sure. I mean, yeah, we could take this, or we could take this right now and say, so what do I got here? I've got a third and a pi and an r in everything. So I have this, a third and a pi and an r, and a third and a pi and an r. So this is an h and a 2 and a dr dt and a r and a dh dt. Sure. I mean, essentially that's what it would look sort of like. Okay. So we're not going to go too much further down this rabbit hole because I'm thinking right now I've convinced you, like, oh, please show me another way. Because this is a lot, and I'm about to make you even sadder. If we go up and look in the problem, I have this rate. So 9 cubic feet per minute represents what variable or what expression in this relationship? Where would that 9 go? If I wanted to start plugging numbers in here. 9 cubic feet per minute, what is that? That's, okay, it's not the volume, because it's 9 cubic feet per minute. It's the change of the volume. Yeah, it's dV dt. So that'll be a 9. That's the height. They're asking us for dH dt, and we don't know what dr dt is. So that's a second wrinkle in this problem. If we try to do this with a product rule, that's great, but I don't have an R. I don't have a specific R for 6, and I don't have a dr dt. So how in the world are we ever going to get through this problem? No fear. There's a friend right around the corner to help us. So let me talk about this friend for a minute, and then we'll come back to our problem. Every time we would stop and have a circle and a height, you would have basically something that would look like that, right? You have a radius and a height and a slant. You have a radius and a height and a slant. You have little ones and progressively bigger ones. Okay. Horrible picture. You can see that though, right? Like there's these right triangles. So as you put more water in the tank, essentially we've got this right triangle relationship that's happening. And normally, when we get to the end, that's 5 and that's 10. We want to talk about the point when, I think it says 6. Yeah, when the height is 6. Okay. And this would be like a little peepee one with like an R and an H. Talk to me about these triangles. They're all right triangles. They all have a 90-degree angle. They all have the same angle at the bottom because they all kind of hit right here. So if I pull the triangle out, this little angle down here is the same angle whether it's in the little peepee guy or the bigger guy or the all the way up guy. So it's got this angle the same and this angle the same. So that would have to mean that these angles are the same. Your geometry teacher's sitting somewhere with their fingers crossed, hoping. If all 3 angles are congruent, from this triangle to this triangle to this triangle, then my triangles are similar, which means what? In your heart, if you had to guess a number for X, what would you guess? In your heart, look at that. I heard somebody whisper it. What would you guess? I'd guess 3. Why? Why? Okay, and that's what's here. So that's what has to be here because similar triangles, your sides in the similar triangle have to be in a fixed ratio. So since this side is one leg to the other is 5 to 10 or a half, then this one would also have to be the same as 5 to 10 or a half. And if X to 6 is a half, then X would be 3. Awesome. So that means that R to H is a half, or 5 to 10, if you want to look at it that way. Okay? And that's always true. So how about 2R is equal to H all the time? Yeah? No? In this problem, whatever height we stop at, the radius will be half as much. Or if you double, anytime we stop, whatever the measurement is for double the radius, the height will be that measurement. Now, here's why that makes us super happy. I now have a relationship between these two variables. Either I can say 2R equals H, or R equals H over 2. I can replace one with the other. I could take H's out and replace them with two R's. I can take R's out and replace them with H over 2. These are two different substitutions I can make in my formula. Okay, here's the nice thing. Once we've fought through this cone problem, all the cones are the same. They're not all 1 to 2, but there's always a fixed ratio. So if I'm doing a cone volume problem, I can always start with figuring out, well, what's the relationship between R and H? We had to kind of dig through all of that in this first problem. You're going to practice more cones. Okay? They're the tough ones. Sometimes that show up, and so you'll see a couple more cones running along here, not in today's packet, but in your homework assignment and in the review packet and so on, because that would tend to, that's also probably very indicative that you're going to get assessed on a cone problem. Okay, so let's go back to this horrible thing. Yuck. I don't want all that. Let's go back up to here. I want dH dt. That's what I'm looking for. So I'm thinking I'd like to write this function only in terms of h, because then if it's just v and h, when I take my derivative, I'll have dv dt and dh dt, and that's what I want to focus on. That's what I'm looking for in this problem. So my choice, because of what the problem was asking, is I'm going to take my v equals 1/3 pi r squared h. Okay, I'm going to take the fact that r over h was 1 over 2, or h equals 2r, or h over 2 equals r, and I'm going to rewrite my function like this. Okay, make sure you process that. Make sure you're okay with, all I did was rewrite it. And I'm going to clean this up a little bit. How about that's 1/3, that's a pi, that's an h squared over 4 with an h. So how about a 12th times pi times h cubed? That's an alternate way to find the volume at any given point on this cone. I can find the volume just from the height, because I know in this particular cone, half the height is equivalent to the radius. And that relationship is consistent no matter how much water I put in the cone, because of similar triangles. So however much water's in that cone, whatever point I stop, the height and the radius of the circular surface are in this ratio. The radius to the height is going to be in a ratio of 1 to 2. In this cone, please do not memorize this and then use it on another cone problem, because I could give you a totally different cone with that's big and short and has a different ratio between radius and height. Remember that you can set up the ratio of the radius to the height, and that's how you can relate them. It was a 5 and a 10 specifically that created the half. It's not a half for every cone. All right. That's the hardest problem you're going to do. The cone problem is always the hardest problem. It made sense for us to do it after the tank just because it's another volume. The other two problems we're going to do today are both right triangle related. So they're going to have a slightly different approach as we look at things. We'll be focusing on Pythagorean theorem. So here we go. dv dt equals 3/12 pi times h squared times dh dt. I only had one function there, h cubed times the constant pi over 12 or 1/12 pi. So I didn't have to use any product rule. If you're wondering, I'm going to just skip back here for a minute. I'm sorry, I keep jumping back and forth. But if you're wondering, like, could we do this? We could have. We could figure out, we would have had to figure out how dr dt and dh dt are related. At some point, we would have had to get that 1/2 relationship. And that would have to come into this problem in order to solve the equation this way. We'd have used our height of 6. We would have had to figure out that the radius matching would be 3. And we would have to also figure out that the rate of change of the height, if 1/2 the height is equal to the radius, then 1/2 the rate of change of the height is equal to the rate of change of the radius. So that's how we would have had to still get to that problem. We would still have to connect the radius and the height to make this problem work. There was no getting around that because we didn't know how radius was changing. But we're good. We're right here. And that's 9 cubic feet per something or other minute. And that's 3/12. And that's pi. And that's 6 squared. And that's dh dt that I'm looking for. It's highly likely this is going to be in terms of pi. So calculate around the pi. You're going to have a calculator, so you know the arithmetic here doesn't have to totally stress you out, but we should be able to roll that pretty easily. I'm sorry. So 9 cubic feet per minute is equal to 9 pi, actually 9 pi, square feet, because the 6 was feet squared. 6 was feet and we squared it. dt. So once again, be careful. 1/pi foot per minute is dh dt. Make a little note over here. So it was 3/12 times pi times 6 feet times 6 feet. And so that's how we got our square feet over here. That 6 was squared and that 6 was foot. Think about what you're measuring the change of. The units should match the kind of thing you're measuring. If it's a height or a length or a width, it should be in a linear unit. A foot, feet per minute. If it's an area, it should be in square feet per whatever unit of time. If it's a volume, it should be in cubic feet per minute of time. So linear unit, a radius, a height, a length, a width, all of those things are single units of length versus square units if we're looking for an area change, or cubic units for a volume change. Okay.
Could you re-explain that?
re-explain the units?
Yeah, I'm just trying to understand how you went from get the 1 over pi. I know you did pi out, but how'd you get the 9 on the other side? I know it's feet squared.
Okay.
But how'd you get
Yeah,
the
I did
pi?
that too. Okay, so it's 9 cubic feet, and then this was
1/4.
yeah. So you're okay with the 1/4?
Yeah.
Okay, and then 6 squared dHdt.
Okay, I understand.
Okay. I don't know why I do that all the time. I don't even know how I do that all the time. Okay. You alright with that? And, oh, I left the pi off. Pi. I say this all the time because I do stuff like this all the time. 9 feet cubed equals 9 pi feet squared dH/dt. It's like I get so close to the end that I lose my mind and I just look at that and I go, 9 pi, divide it, pi. It's not pi. If I don't write it down, if I just try to do it in my brain, I often flip things around and do them in the wrong order. I am dividing by 9 pi. I want to isolate this. So if I divide by 9 pi square feet, the pi is in the denominator. 1 over pi. And you better believe if that's a multiple choice question, pi will be there. Absolutely. 1,000,000% guarantee. If this was a multiple choice question, one of your choices would be pi feet per minute. And you would look at it and go, yay, I got it. And you'd pick it and you'd feel happy. And then you'd get your test back and be like, oh, crap. Right? Try to finish strong. Don't hurry up. Don't try to showboat your way to the end. Divide both sides, look at what you got, slow yourself down to make sure, you're almost done, so you're super excited, and you're like, I'm almost there, especially when you look and you think, you're like, I feel it, because I see my answer, or what I think is my answer. Those good answers are there to distract you. That's what makes a multiple choice test harder sometimes. Okay. Now we got the cone behind us. All we got left is Pythagorean theorem. We'll do the Tweety problem. We probably won't get to do the rowboat problem, but I'll draw you the picture for the rowboat problem. The rowboat problem is just another problem, just like the Tweety ladder problem. It's a right triangle problem. Okay. So, we got the bird. And we got a ladder. And we got the ground. Okay. And this is where we're going to make not assumptions, but there's going to be some things we're going to have to kind of go with that make the problem solvable in the way we're going to solve it. And so one of those things is that when we talk about stuff up in the air, height is a measurement that is perpendicular to the ground. So we are always, when we're measuring height, perpendicular to the ground, that is a 90-degree angle scenario. Okay, we don't worry about this being on a hill and this being like we're like 90 degrees. That's where we're living. So anything that's up here, it's a 90-degree angle. Now, here's what's happening. The bottom of the ladder is getting pulled along the ground, and the top of the ladder is sliding down. Okay? And we're waving our hands at a whole lot of physics in this problem, okay? So, we're assuming, making a lot of assumptions, that the ladder is moving backwards, and as it moved backwards, it stays leaned up against the pole. And so as things get pulled, we might be looking at something like this. I'm going to draw this. I'm going to try to, okay. So I really like drawing it on the same picture, but I'm not going to. Okay. Oh, no. Okay. Sorry. Talking to myself. So here's what's happened. That's the ladder. And the bird's up here. And this is the ground. And so this was an X. And that was a Y. And this is a different X. And this is a different Y. In two right triangles. And the thing that doesn't change is the length of the ladder. As the ladder gets pulled and is sliding, we have the exact same length of ladder. We are maintaining a right triangle relationship as the bottom of the ladder is pulled this way, which means the top of the ladder is falling. We are sticking with a right triangle relationship. So whatever X is plus whatever Y is equal to whatever Z is. And Z is going to be my ladder. Z is constant, right? Z is the ladder. So when I take the derivative, 2x dx dt plus 2y dy dt equals 0. Why 0? So the constant, take the derivative of a constant, you get 0. Okay. Now, X and Y are both changing. X, as we pull the ladder, X is going to get longer and Y is going to get shorter. Yeah? Are we okay with that? So if it goes, if this slides down and this gets pulled in, it's maintaining the right. Just like I said, lots of like suspension of disbelief here. As this comes down, the triangle that it creates gets a smaller and smaller Y and a bigger and bigger X until we have no triangle. We have all this information about the original, where the birdhouse is originally is, and what the ladder is. The ladder is 26 feet long. We're going to need that. But let's continue on the problem and see what we do know. Sylvester's trying to steal Tweety. Hector the dog is pulling the ladder away. So this is the sliding ladder problem at a rate of 2 feet per second. Okay, so what is changing at a rate of 2 feet per second? Which measurement in the triangle is changing by 2 feet per second? Let's see. Hector's pulling the base of the ladder away from the pole. He's pulling this at a rate of 2 feet per second. So the 2 feet per second is how x is changing. How fast is the ladder falling? That is how y is changing. What's the 10 feet off the ground thing? Ian? That's the y here in phase 2, right? So we're talking at a y as 10 in this scenario. My ladder is always 26. So if I look at my relationship that I've taken my derivative of, I need this x. If I get that x, I've got dx dt, I've got y. This is what I'm looking for. So this is what the problem's about. But I'm gonna need x to finish this problem. So how are we gonna get the other x? This is 26. This is 10. How are we gonna get that x? We're gonna use Pythagorean theorem, yeah. And it's 24. I'm gonna cut you to the chase. Okay, so this is 24. Uh-huh. It gives you that, but you don't necessarily know that that 24 is going to be the 24 that happens here. You don't necessarily know that, so don't assume that. This could have been an 8, and then this would have been something different, and this could have still originally been 24. Okay? So this is originally 24, and this is originally 26, and we actually don't really care what this is originally. What we care about is when we get to this point, when this is 10 and this is 26, it just happens to be that this is, in fact, 24. Okay. So 2 times 24 times 2 plus 2 times 10 times dy dt is going to equal 0. Now, didn't do a great job of writing any units in those, so let me float that over with some units. Let's shrink this down for a minute. Okay, so the 24 is feet, and this 10 is feet, and this 2 is feet per second. So this ends up being 96 square feet per second plus 20 feet dy dt equals 0. Okay. Solving for dy dt, 20 feet times dy dt equals negative 96 square feet per second. So when I divide by the 20, boop, boop, dy dt is whatever negative 96 over 20 is. What is it? Negative 4.8. Thank you. Negative 4.8. And this feet, cancel right on these feet. Why is this rate negative? Because it's getting smaller. Yes, it's falling. Y is getting smaller. So things that are getting smaller have a negative rate of change. If we have a tank and the water is leaking out of the tank, the volume is changing at a negative rate. We would have to think about a negative rate of change. If we are, putting two things closer together and the distance between them is getting less, that's a negative rate of change. Positive rates of change are when things are getting bigger, right? Things are increasing when their derivative is positive. A positive rate of change means that item is increasing. A negative rate of change means that item is decreasing. So as X is getting bigger, oops, what happened? Sorry. There we go. No. Let me just make sure I did. There we go. Okay. Crap. Where are we? Oh, we're here. Okay. Oh, and then I cut it and I went right here. Okay. So as X is getting bigger at a rate of 2 feet per second, Y is getting smaller at a rate of negative 4.8 feet per second. Just because one variable is changing at one rate doesn't mean that the other variables are changing at the same rate. That's basically one of the reasons we have calculus, is because Newton wanted to study that. He wanted to talk about, okay, how is the rate of change in one variable affect another? How does, if you speed up the change in one, how does it change something else? Those rates are related, but they're not identical. And a rate, especially that's continually changing, that effect is continue to change over time. So we're always talking about, this is what's happening at one point in time. At this one point in time, the Y side is getting smaller at this rate. Okay, let me draw you the rowboat problem as best I can remember how it works. All right, so the boat's like this, the rope goes like that, and like that, and so essentially we're kind of looking at a right triangle. This is my rowboat, okay, and this is the dock. Actually, I didn't do a very good job there. Nope, the dock would have to be up. Sorry, guys. I'm doing a crappy job. It'll be on the... I suck at this problem. Okay, so there's the dock. Because the ring is up at the dock. And so the rope is getting pulled in, and the boat is coming to the dock. So actually, in this case, it's a right triangle, and two things are getting smaller in the right triangle. I loved calling that X and that Y and that Z. That's my favorite thing to do. Rope. So what's not changing in this problem? What's not changing? The boat's coming in, the rope's getting pulled. That Y's not changing. That's not changing. Okay? That's the picture for problem 4. You also need one of these, and you can grab it on your way out, which is the homework problems. So this is your related rate practice. All the homeworks that have been assigned are going to be due on the 28th, so the worksheet And the textbook problems. Gonna give you a big hunk of homework. Thursday after school, yes, that's fine. Oh, wait, yeah. No, yeah, next week, that's fine. Sorry, I got it. I was thinking it was early. Okay. Everybody get a homework? Yeah. You weren't here for the first part of it?
No, I was. It's just that I didn't have my folder that day. I think I lost.
There you go.
Thank you.
You're welcome.
Oh, the homework class.
Oh, the homework. Oh, okay. 28 homework. Give me not organized. Let's see. Okay. Right, you're welcome. Anybody else not get the theorems of derivatives homework last time? I know. Oh, I'm still recording. Ooh, that was it. That was all.